better now. And we see also the cursor.
Okay, so thanks for having me. I want to talk about infinite distance limits in n equals to Quiver gauge theories, which is based on this work that appeared early this year in collaboration with Hagedorn Infante. So people have learned that spatial loci in field space provide useful information about physics. Examples of these points are symmetric points in the interior of the moduli space, or infinite distance points at the cusps of the moduli space. And today I want to talk about infinite distance limits of the conformal manifold of CFTs. A CFT may admit a conformal manifold, which is parameterized by a set of exactly marginal couplings. And on this conformal manifold, there are free limits, which are Poincare cusps with hyperbolic metric and sit at infinite distance. Now, CFT distance conjecture has three claims about these points. First, that there is an infinite tower of higher spin currents that are becoming conserved in these points. Second, that the higher spin points are at infinite distance. And finally, that the masses approach zero exponentially with this order 1 constant alpha, which is equal to square root of 2 times central charge of the CFT over dimension of the gauge group that is becoming free. Now the plan of this talk is as follows. We are going to study infinite distance limits in SU Quiver gauge theories with hypermultiplets in fundamental and bifundamental representations. We're going to mostly focus on linear quivers and holographic quivers. And we are going to use the large N Hagedorn temperature and the exponential rate alpha as proofs of bulk physics. We are going to argue that the large N Hagedorn temperature has information about the bulk string background. We are also going to study the exponential rate alpha, which identifies the light tower. We are going to find some sharp bounds on it. And we are going to use the convex hull technology to visualize the towers that are becoming light in different directions. And this study is in the realm of the holographic swampland, which is a study of the features of the CFT in order to gain information about the dual, the physics in the bulk dual. Let us begin with a calculation of the Hagedorn temperature. Hagedorn temperature can be calculated from divergences of the partition function of gauge theory on S3 times thermal circle. It is given by this matrix integral that you see here. The measure is the so-called R measure. I runs over the gauge nodes. R runs over the representations. These ZRs are the so-called one-particle partition functions, and Chi's are the characters. And when you are at large N, you can take the continuum limit by doing a change of variables and introducing distribution functions rho I. Sorry. So we first do the calculation for linear quivers. Linear quivers are a chain of gauge nodes connected by hypermultiplets in bifundamental representations. And also each node can have Ki flavor hypermultiplets in the fundamental representation. If we simplify the matrix integral that we saw in the previous slide for these quivers, we find that it is given by a Gaussian integral over these variables rho IL, which are Fourier transforms of the distribution rho that we introduced earlier. And here this matrix ML is given by 1 minus Z adjoint on the diameter. And on the interior adjacent to the diameter, we have minus Z bifundamental. we can explicitly write down the determinant of this matrix, and then Hagedorn temperature happens for the first zero of the determinant, which is the first blow up of the partition function. By first, I mean the smallest temperature. So we find this equation highlighted here in pink for the Hagedorn temperature, and this equation has a striking universality. It depends only on P, which is the number of gauge nodes. And in particular, it is independent of the ratio of the ranks, ratio of the NIs, and also of the flavor distribution. Let's keep this result in mind and study brain model realizations of this quiver. In type 2A string theory, this quiver is realized by P plus 1 NS5 brains, and between each pair of NS5 brains, you can have NI D4 brains and KI D6 brains. And if you take this construction and take the LS goes to 0, GS goes to 0, delta X goes to 0 limit, while keeping the gauge couplings fixed, you will find exactly the linear quiver that we were talking about. Now, if one calculates back reaction of this construction, one has in principle bulk dual to the quiver, which is a difficult thing to do. However, we note that tension of the NS5 brains is much larger than tension of D brains here. Therefore, it is natural that the background string theory is determined by the number of NS5 brains. And then the D brains, etc., are like defects on top of this background. This expectation is verified for P equals 1 by Gade, Pomoni et al. Taking this result and combining it with the result from the previous slide, we conclude that Hagedorn temperature contains coarse-grained information about the string theory in the bulk, while it is not sensitive to the defects. Now we can also proceed to test this idea or this conclusion for holographic quivers. Holographic quivers are large N quivers with central charge A equal to central charge C, or number of vector multiplets equal to the number of hypermultiplets. We can also denote the number of hypermultiplets connecting the ith and jth gauge node by Aij, and these will be entries to the so-called adjacency matrix of the quiver. For a balanced quiver, this requirement NV equals NH leads to this condition, n dot k is much smaller than n squared. And this leads to affine ADE quivers, which I have drawn here. We have the A-type quiver, D-type quiver, and E-type quivers. Or we can have a quiver with infinite number of gauge nodes, as long as a holographic quiver with infinite number of gauge nodes, as long as the ratio of the Ki over Ni is order 1 only for a finite number of nodes. Having classified these holographic quivers, we can move on to calculate the partition function. The calculation will go through as in the case of linear quivers. And again, we have a Gaussian integral. And now this matrix ML that we had before is given by 1 minus Z adjoint times unit matrix minus Z bifundamental times the adjacency matrix. The Hagedorn temperature happens for is the first blow up, which is the first zero of the determinant, which corresponds to the maximum eigenvalue of the adjacency matrix A. Now, interestingly, we have from mathematics, we have inequalities, two inequalities on this lambda maximum eigenvalue of adjacency matrix. And we noticed that for holographic quivers, this minimum of Ki over Ni is 0. Also, this n dot k over n squared is 0. And these together pin lambda maximum to 2. We can plug it back here, and we get that Zv plus 3 Zc is equal to 1. This is exactly the equation that you would get if you were to compute the Hagedorn temperature for n equals 4 super Yang meals. We therefore conclude that this Hagedorn temperature is diagnosing the 10D type 2b string while remaining insensitive to the geometric details such as orbifolding. Okay, so we calculated the Hagedorn temperature for linear and holographic quivers and came to a consistent conclusion in both cases. Now we will move on to the exponential rate alpha. We said that this exponential rate is given by square root of 2c over dimension of the gauge group that is becoming free and identifies the leading tower. This alpha will have its minimal value in the overall free limit that all the gauge couplings are going to 0. We denote it with alpha mean, and it is equal to, it can be written in terms of the central charges A and C, and it is equal to 1 over square root of 2 times 1 over square root of 2A over C minus 1. Now we want to bound this alpha minimum from above and below. If we calculate the ratio of number of hypermultiplets over vector multiplets, it is equal to 1 plus something positive, also equal to 2 minus something positive. Therefore, it sits between 1 and 2. We can translate it to a bound on A over C. And also using this equation for alpha minimum, we can finally get the bound on alpha minimum. Alpha minimum is bigger or equal to 1 over square root 2 and smaller or equal to square root of 2 over 3. And this lower bound is saturated for holographic quivers, which have A equals C. Okay, and also this is the minimum value for alpha, so we can promote this to a bound on alpha, which is that alpha is bigger or equal to 1 over square root 2. This is a bound that was proposed in the paper by Perlmutter, Wafa et al. And now we are here proving it for quiver gauge theories. Okay, so now we can use some of this convex Hall technology to go beyond the overall weak coupling limit and visualize different towers that are becoming light in different directions on the conformal manifold. People define these charge to mass ratio vectors, alpha, which is equal to minus gradient of log of mass of the tower. Here we have the metric. We can calculate the flat coordinates. And also mass of the higher spin tower goes like square root of anomalous dimension, therefore goes like GI. And given these two last pieces of information, we can calculate the alpha I vectors. Alpha I vectors are given by square root of 2c over dimension of GI times delta I. We find the taxonomy rule that delta and that alpha I dot alpha j is equal to 0. Therefore, for these quivers, the alpha vectors are perpendicular to each other. And we have also plotted these alpha vectors and the part of the convex Hall, the simplex given by these vectors for some simple examples. The first one is SUN circular quiver. We see that the alpha vectors have the same length. And also we see that the side of the simplex is touching the radius 1 over square root 2 circle, which is a signal that this is a holographic quiver. Also, we've plotted it for linear SUN quiver. Here again, the alpha vectors have the same length. However, the side of the simplex is not touching the circle. We also plotted it for SU2N quiver. As one would expect now, the alpha vectors don't have the same length, and the side of the simplex is not touching the circle, which means that it's not a holographic quiver. Okay, and then one could ask the question if these two probes that we are using, the Hagedorn temperature and alpha, have any correlation. In order to see that, we can use a simple example. Take the quiver SUN to the P and the quiver SUN times SU2N up to SUPN. We can calculate alphas for these quivers, and we can easily see that we can have quivers with the same Hagedorn temperature, but different alpha, the same alpha, but different Hagedorn temperature, which leads us to the conclusion that the relation between alpha and Hagedorn temperature is many to many. Here there is a simple explanation for this, and that is that the states that are saturating the Hagedorn temperature do not necessarily decouple from ADS scale, do not necessarily become exponentially light as we approach the infinite distance limit. All in all, the Hagedorn temperature and alpha are providing two probes for us that give information about, distinct information about the bulk physics. One is giving us information about the string background. The other is giving us information about the leading tower. Okay, and finally, let me conclude. So we computed the large and Hagedorn temperature and exponential rate alpha for SU quivers with hypermultiplets in fundamental and bifundamental representations in the infinite distance limits. We argued that the Hagedorn temperature informs us about bulk string theory. It has coarse-grained information and is insensitive to the geometric details. Also, we studied the exponential rate alpha, which identifies the leading tower. We derived bounds on it, and we went beyond the overall free limit and used this convex hull technology to visualize the towers that are becoming light in each direction. Also, we saw that the correspondence between the Hagedorn temperature and alpha is many to many, meaning that these are probes that provide two distinct pieces of information about the bulk physics. Yeah, thank you so much for your attention.
Thank you. Are there any questions? If not, in the meantime, maybe let me start. Florent, yeah, please go on.
Yeah, sorry. Very nice talk. For the taxonomy rule alpha I dot alpha j equals 0, is it something you, let's say, something you noticed, or do you have an explanation for why it should be like this?
This is something we derived. Because we derive the alpha I vectors, and if you calculate the dot product, it will be 0. And this is a consequence of the fact that if you have a tower whose anomalous dimension gamma goes like G1, G2, say, that will not be the leading tower, because you have one of these, say G1 going to 0 faster than G2, and therefore the tower given by G1 squared is lighter than the tower given by G1, G2.
Okay, cool. Thanks.
I also had a quick question. So you said it for holographic quivers, if I understood correctly, the bound is saturated, but is that because, is there a reason why this is the case that you would expect a priori, or?
Yeah, because in that case, the central charges are equal. Yeah, I think you can also have some interpretations from the bulk dual exponential rates, but here let's say that we expect it because in case of holographic quivers, the two central charges are equal.
Okay, thanks. Any other questions? Well, if not, I will end the recording, but feel free to hang around and ask the speakers more other questions more informally, maybe. And thank you again for the talk.
Yeah.